Alright, in this video we're going to look at something called the factor theorem. What the factor theorem is going to do is allow us to factor polynomials of larger degree than 2. I'll just mention this on the side. In grade 10, you learned to factor quadratics, x squared plus whatever, 7x plus 10. Right? You know how to factor that into by doing simple trinomial factoring. What numbers multiply to give you 10 and add to give you 7, so that'd be 5 and 2. So we were able to write this quadratic as a product of two linear factors. Okay, so we know how to do that for quadratics, right? That was, grade 10 was a huge unit in grade 10. But we don't know how to do it for cubics, right? If the degree was 3 or cortex degree 4 or anything higher than 2, we don't know how to do it. So we're going to need some other way to do that. And the way we're going to do that is using what we call the factor theorem. So what the factor theorem tells us, so the factor theorem says if p at x, if p at a is equal to 0, then x minus a will be a factor of p at x. Okay, so just to illustrate what this is, not to prove it, but to just give you an example of what we mean, let's just look at this example I did up here, just a simple quadratic example. So in this example, p at x would have been the quadratic here, x squared plus 7x plus 10. So we know that x plus 5 and x plus 2 are factors of p at x. So what the factor theorem tells us, this rule right here, it tells us that if we substituted a into this polynomial, we should get 0. Okay, so what is a? Well, a is the number that you're subtracting here. Okay, so in this case, for x plus 5, the a value would be negative 5. Like, what number are you subtracting? Well, you're not subtracting a number, you're adding a number, and then when you add a number is you subtract a negative. So we're subtracting negative 5. Okay, so what the factor theorem tells me, if I sub a negative 5 into my polynomial, I should get 0. So negative 5 squared is 25. 5 times negative 5 is negative 35 plus 10. Lo and behold, it is 0. And it should work for the other factor too, right? For the factor of x plus 2. A was equal to, in this case we're subtracting a negative 2. So p at negative 2 is equal to negative 2 squared plus 7 times minus 2 plus 10. So 4 minus 14 plus 10 is again 0. So in both cases we get 0, which is that shouldn't be a surprise. That's exactly what the factor theorem told us, right? If you evaluate a function at 0, then that means that x minus a is a factor of that function, or of that polynomial. It only works if it's a polynomial. So now I'm just going to prove it quickly. So proof. And the proof is basically just a result of the remainder theorem. So recall the remainder theorem, which said if p at x is a polynomial, then the remainder when p at x is divided by x minus a is the function evaluated at a. So that was the remainder theorem. So basically, the factor theorem means that, well, one other thing you need to know. Okay, so if x minus a is a factor of p at x, then the remainder when p at x is divided by x minus a is 0. And that should be obvious if you understand what a factor means. A factor is a number. Right? A factor means that p at x would be equal to x minus a times some other terms, right? Times, we'll just say q at x. If it was a quadratic, this would just be one other linear factor. If it's a cubic, it would be two linear factors, or a quadratic factor. So that's, but notice there's no remainder, right? If it's a factor, then there won't be a remainder. Well, if we put these two things together, if the remainder must be 0, thus if x minus a divides p at x with a remainder of 0, then by the remainder theorem, p at a must be equal to that remainder, which was 0. But this is exactly what the factor theorem said, right? This is what we wanted to prove with the factor theorem, that if x minus a divides this, then the remainder is 0, so p at a is 0. Therefore, well, basically the theorem's true. Therefore, if p at a is 0, then x minus a divides p at x with a remainder of 0, meaning it's a factor. Which is what we wanted to show. Okay, so proved.